Welcome back. Now I am going to explain on simple harmonic motion, that is SHM. It comes under module Oscillation and Views. The video question on this topic goes like this. The first question: define simple harmonic motion, mention its characteristic, derive an expression for differential equation of simple harmonic motion. Okay, now we'll start with the simple harmonic motion now. So this discussion starts with the periodic motion. What is periodic motion? A motion which repeats itself at regular interval of time is called a periodic motion. A motion which repeats itself again and again at regular interval of time is called a periodic motion. For example, uniform circular motion is a periodic motion. Simple pendulum is also a periodic motion. So why I am discussing this periodic motion is, so the simple harmonic motion is also a periodic motion there. Okay, so it's a general term there, periodic motion. Next comes oscillations and vibration. What is oscillation and vibration? A particle in a periodic motion moves back and forth over the same path, then it is called oscillatory or vibratory motion. If a particle in a periodic motion moves back and forth over the same path, then it is called oscillatory or vibratory motion. For example, simple pendulum. The pendulum bob moves back and forth on the same path. So such vibrations are called what? Oscillations or vibrations. Such motions are called oscillations or vibration there. Okay. When you use the word oscillation, when you use the word vibration, meaning is the same there. So when the frequency is less, okay, so then it's called oscillations. So for example, simple pendulum. So if the frequency is more, then it is called vibration. For example, the string of a guitar there, or string of the violin, or the vibration of the atoms in the molecules comes under what? Vibration. So if the frequency is less, then it is called oscillation. Meaning is the same. So you have to remember when to use the word oscillation, when to use the word vibration there. Okay. So what we call oscillations and vibrations. Okay. So examples are pendulum, motion of the mass suspended to spring mass system. So violin string and atoms in the molecules comes under vibration there. Okay. So oscillations and vibration. So next is the simple harmonic motion. We shall start with one example, what we call spring mass system. So consider a mass which is connected to a spring and it is free to move on frictionless horizontal surface there. Frictionless horizontal surface. Okay. So now if initially it is at rest, it has not been stretched there. It is at rest now. If I stretch the mass little bit by applying the force towards right, okay, through a small distance x, for example, okay, by applying the force, after stretching, if I release, it starts moving back and forth there. Okay, what we call simple harmonic motion. So this type of oscillatory motions are called simple harmonic motion. What is the definition of simple harmonic motion? Why the mass comes back to its original condition, that is equilibrium position, again goes to the minus x, plus x, minus x, plus x, minus x there. Since it's frictionless, it keeps on moving indefinitely there, right? Okay. So now, why it comes back to the equilibrium position and why it oscillates back and forth then? Okay. So because once if I stretch the mass through a small distance, so restoring, you know that action and reactions are equal and opposite. A restoring force come into play, so within the spring, which tries to bring back the mass to the equilibrium position there. Okay. So that means restoring force F I have shown here is proportional to displacement. Restoring force that has been developed in the spring, when I stretch the spring there, restoring force is proportional to displacement. X is the displacement there. Okay. So that means F is equal to minus Kx. K is the proportionally constant there. F is equal to minus Kx. How the minus has come here? So minus indicates that the restoring force is proportional to displacement and is acting in a direction opposite to the displacement. Okay, that's why minus here, acting in a direction opposite to the displacement there. So this is the definition of simple harmonic motion. F is equal to minus Kx. We can make one small definition here. Simple harmonic motion is an oscillatory motion. It's a periodic motion or oscillatory motion in which the restoring force is proportional to displacement and is acting in a direction opposite to the displacement. So this is one definition of simple harmonic motion there. Okay. Now also from the Newton's law, F is equal to ma. F is equal to ma there. Okay, mass into acceleration. Now both are F there. You can equate equation number 1 and equation number 2 here. Equation 1 number is equal to equation number 2. That means minus kx is equal to ma. A is equal to, so rearrange the equation, minus km divided by x. K is the proportionality constant. If it is spring, it is spring constant. If it is not spring, it is called force constant there, right? Okay, so minus k divided by m. M is the mass there. So this is constant there. So this is constant there. What it indicates? A is proportional to x. You have to put minus here. Minus is there. Okay, A is proportional to minus x. That means acceleration is proportional to displacement and is acting in a direction opposite to the displacement. So this is another characteristic of simple harmonic motion. Okay, again you can make one. That means in simple harmonic motion, acceleration is proportional to displacement and is acting in a direction opposite to the displacement. This is another definition of simple harmonic motion, or another characteristic of simple harmonic motion. Again I can make one more definition here. Simple harmonic motion is an oscillatory motion in which the acceleration produced in the body is proportional to the displacement of the body from its equilibrium position and is acting in a direction opposite to the displacement. This is another definition of simple harmonic motion. Okay, together we can make one definition. Definition of simple harmonic motion. Simple harmonic motion is an oscillatory motion in which the restoring force is proportional to the displacement, or acceleration produced in the body is proportional to displacement of the body from its equilibrium position and is acting in a direction opposite to the displacement. Okay, this is the definition of simple harmonic motion. Okay, remember this. Next is differential equation of simple harmonic motion. So we'll use the same formula that used in equation number 1. F is equal to minus kx. Ka is the proportionality constant. If it is spring, it is spring constant. If it is not the spring, it is called force constant. F is equal to minus kx. Also, F is equal to ma. F is equal to ma there. Okay. So what is ma? Acceleration. What is acceleration? D square x by dt square. X is the displacement. D square x by dt square. So equate these two equations there. M d square x by dt square is equal to minus kx. Okay. So rearrange the equation. D square x by dt square plus k by m is equal to x. So this is the differential equation of second order. I can put it in the standard form there. So d square x by dt square plus, I will take this term as omega square. Omega square x is equal to 0. Okay. What is omega square here? Omega square is equal to k divided by m. This k divided by m is taken as omega square there. Okay. So this is the differential equation of simple harmonic motion. D square x by dt square plus omega square x is equal to 0. Okay. So now, what is omega here? Omega is nothing but angular frequency. Angular frequency. So it's equal to what already are taken. So root k by m. What is k here? Spring constant if it is spring, otherwise force constant. Okay, general term. M is the mass suspended to the spring. Omega is also called natural frequency of vibration. Find the natural frequency, or to use this formula. Omega is equal to root k by m there. Okay, angular frequency. You know that once if I know the angular frequency, I can calculate the linear frequency, because omega is equal to what? 2 pi nu. 2 pi nu there. Okay. So general solution of the differential equation. Differential equation that we considered in the previous page there is given by x is equal to a e to the power of I omega t plus b e to the power of minus I omega t. This is the general solution. General solution can also be written as x is equal to a sine omega t plus phi. Okay. So what is phi here? Phi is the angular displacement at t is equal to 0. So if I know the angular frequency, I can calculate the time period. What is time period? Time period is given by t is equal to 2 pi by omega. 2 pi 1 upon omega means what? Root m by k. Remember, it is omega is root k by m. Omega is in the denominator, that's why root m by k. Remember these two formula. Expression for angular frequency and expression for time period. Numerical will be asked based on this, so we shall solve later stage there. What are the characteristics of simple harmonic motion? So, okay, so whatever you understood, you list out. That itself is the characteristic of simple harmonic motion. Simple harmonic motion is a periodic motion. Remember, simple harmonic motion is also a periodic motion, right? It's a periodic motion. Here, the oscillating system must have inertia. That means there should be some mass suspended to spring, right? So, oscillating system must have some inertia. That means mass should be connected to the oscillatory system there. Okay. Acceleration is proportional to displacement and is acting in a direction opposite to the displacement of the body from equilibrium position. Okay. The frequency and time periods are independent of amplitude. Okay. So here t time period there. angular frequency omega is equal to root k by m. So there is no term related to amplitude there. That means frequency and time periods are independent of amplitude. Amplitude may be less or amplitude may be more in a simple pendulum, but time period of this simple pendulum remains same. So larger oscillation and smaller oscillation have the same period there. Okay, you might have observed that when the simple pendulum, the bob of the pendulum making a smaller oscillation, it moves fast. If the amplitude is less, it moves fast. If amplitude is small, it moves. If amplitude is small, it moves fast. If amplitude is less, it moves slow there. That means the time period remains same there. Okay, so now what are the example? The spring mass, example of simple harmonic motion, the spring mass system, tuning fork, pendulum, swing, normal swing there. So RLC circuit, in electrical circuit also simple harmonic motion will be there. RLC circuit, what are resistance, inductor and capacitor, series and parallel resonance. There is a trade-off between the electric field and magnetic field between the capacitor and the inductor there, right? Okay, this is the RLC circuit. Okay, these are about simple harmonic motion. So prepare for this. So it will carry 8 marks there.